Drop temperature just a little bit.
It is like, somebody said Navy.
You want a plastic cup or something now?
Big, heavy, this thing is very over engineered.
How much do you want, Chuck? A quart?
Hold on 1 second.
When we talk about being able to improve it.
Marvin?
It could be, we don't need it solid, it could be, out with hollow inside, give it a lot of weight, these kind of things. A lot of ways to improve, what we're doing as far as taking kilowatts, the electric usage down.
Interesting that you had to get it that close, that it has to be that kind of surface area with the size.
Small. We don't know, we think we can
Figure that out better.
No, it's, we don't have a, excuse me, no, we're not, because that's not, the whole patent for shockwave
Yeah. Here's it.
technology, so to speak, making
Put off
thing
some water we can get.
shockwaves, okay, with,
just
spinning
yeah.
device, using centrifugal force to suck the water into the dead and hold. That's what we add in the tolerances and everything. And I think we don't even mention it, because we don't want anybody to know, what they are. Basically takes
Two.
the entire, we think the tolerance is actually really small.
81 degrees, 80 degrees.
The numbers in the thermometer, what do you call it? Thermometer locations, right?
But
Action,
Really, 80 degrees.
fingers are going to put along the top of the skirts on trees, not sitting down in there. We don't.
here, 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 and here. And record. Every 30 seconds.
Oh,
You gotta be quick, boy.
yeah.
All right, how about every
Make sure
minute?
it's not
Marvin?
29 too.
All right.
Just from the beginning to the end,
You gonna keep up with these
Every
temperatures?
5 minutes, you're okay.
They ain't gonna be many 5 minutes in this run.
How long you run?
It's only gonna run probably
Yeah, I
15 to 17 minutes.
Minutes.
That's kind of a watch.
Okay.
All right. What I wanna do, I wanna.
So time is, we're gonna have to be sure we get time very accurate.
Right.
Yes, they go.
All right. Do you want me to walk you through programming this?
No, I'm relying on you to measure electricity because I said from the beginning,
Today
You dropped that class, didn't you?
I didn't drop that class, but I'm not gonna become an electrical engineer today. Are those temperatures changing very much?
Brad not stating.
How often?
We've got a certain probe cut. That probe is the air temperature. Nobody wants to go with that probe. That's all right.
Close, right?
No, no.
I have to put my date on it. This is still November 16th. And we're here at the Rothwell residence in Chamblee, Georgia.
Yeah, of course.
There's the whole family, and let's not forget the famous cold fusion expert, Jed Rothwell.
What about me?
Jed, what are your comments about the experience of the day? Really?
That's about it.
All right. Okay.
Okay, now.
Well, now we're gonna see the magic trick of Aya. Is it
Okay.
better than cold fusion?
Oh, yes. It works.
Alright. Now,
Our
Naomi,
volunteer.
this is my volunteer. You tear this up and then crumble it, and then, okay, tear it up. And just, now crumble it up like this. Okay.
Can I get into Aya?
Thank you. And then I'll put some magic powder on it. See, it's still one, right?
Crumble it down. Okay.
Okay. Now give it back. Open it up.
Oh, beautiful. It's one piece of paper. One
Ta-da!
Yeah.
Very good.
It's smaller.
Oh, it is
That's what
not.
happens sometimes. It had to get smaller because the excess mass had to go somewhere. Oh, hey, you let the cat go upstairs.
Oh,
Oh no! Excuse me.
was the cat going upstairs?
Cut the video!
Yes,
Cut the
and she's gonna
video!
bother
Cut
you
the
while we-
video!
Why? I'm taking a picture of
We
you.
need to get the cat from here.
She's running away. She's
Oh, I do your finger trick.
Don't just say.
Let's get these paintings in, of course. There's one painting. There's another one. Oh,
I come down.
there's another one. A little bit on angles.
She's like a spy.
You didn't get it?
You didn't get her?
Mm-mm.
What are
Yeah,
you
I
gonna
didn't
do?
get her.
We'll get her done by the time you go upstairs to go to sleep.
Okay.
Oh, I don't shut the door.
You don't.
Leave it open.
Okay.
So Naomi, what grade are you in?
7.
7th. And Aya, what grade are you in?
Third.
All right. At least we know what you are for all time.
Okay, I think have to get something from the kitchen.
I should stop filming this and
All
down.
right. All right. The world's worst aircraft. Show me the worst one, Jed.
Oh, that's okay. Stop doing that. I don't want to do something.
All right.
Of course, the nuclear power input should act quite quickly, efficiently. The calorimetric curve should be need to be changing quickly. Here show this figure show our results. You can see here. This is nuclear power input. This is a measure. You can see here, not the same. Here, the input energy going down. Here, still going up. It's not the same. We call this kind of heat generated is anomalous heat generated. There a lot of this kind of here is very clear, and there are so many. Here we change by ourselves from 1.13 milliwatt to 2.5 milliwatts. Here, the measurement curve is like this. But here, not by us, by itself. Their voltage going down. Here it's going up. This is the example. Okay. It's time. Finish it. Okay. Any questions? Sorry.
You can just summarize on this last slide.
Okay.
Summary.
My contribution is can I see here? Our calorimetry is okay, and we measure the enormous heat and excess heat. The current density is this range. Thank you for your attention.
Going already 10 minutes later, and permits only one question. There are no questions. Thank you very much. Now on to the next paper. Excess heat production equation, Dr. Waltman and Dr. Waltman's paper.
Someone at the back, raise their hands if they can hear me. First thing I'm supposed to do is change the title from what the chairman said. I understand those are the rules. So that the title is Excess Heat, the Macro Principles. Now, I'm using the term excess heat the same as has been used here this afternoon, the heat over and above things that are due to known chemical or metallurgical reactions. And instead of using excess heat, use X-heat throughout this paper. First, I'd like to show you some data that's especially brought here from prehistoric times. And just in case you can't see some of it from the back, this medicine man is busy giving one of his boys hell and saying, if I've told you once, I've told you 1,000 times. Don't use fire until I understand it. And I guess the message is quite clear. Now, in this paper, we'll attempt to answer this question. And by the way, I'll start out by saying I accept excess heat. And not that I'm intimidated by all the things that have been said in the next hour or two, but I came here with an attitude. Question is, considering the state of the art, what should one do to accelerate progress to practical use? And the answer must be independent of understanding the details of the heat-producing mechanism. Otherwise, the medicine man will get at me, and I don't want that to happen. Okay, and the answer, which is the rest of the paper, goes something like this, that one should develop and verify macro principles which predict excess heat in terms of controllable state properties of the heat source. If one does that, one is now able to design commercial reactors, and those are our main motives in presenting the paper. Briefly, these are the contents of the paper. First, we'll talk about 3 macro principles, which are principles for predicting X power. Of these 3, the first is a new one. The 2 are principles you'll be familiar with. They're very, very old, but it takes all 3 to make a prediction. We'll then talk about how one simulates this kind of prediction and compare prediction versus experiment for consistency. And the first macro principle is the X-heat production equation in terms of 3 state properties. Okay, now, from the point of view that we're writing this, we don't consider that the system is the electrolytic cell. We consider the system as producing heat is the lattice. In this case, the lattice is the cathode. Now, let's just remember what it looks like. A palladium lattice is a 3-dimensional array of palladium atoms, and in the spaces between the palladium atoms, in the interstices, are hydrogen, deuterium, or tritium. Now, the atoms themselves are all vibrating very high frequency, and we know from the internal energy of the lattice what the frequencies are and what their distribution is at various temperatures. But the important thing that's happening is one other thing. The deuterium is jumping from place to place. Now, this isn't a lazy jump that you do every once in a while when you think of it. This is a very, very rapid jump, and at room temperature it occurs at almost 1 billion times a second. The characteristics of those jumps are the most important thing to understand in order to predict excess heat, and that those characteristics depend on the internal energy. And we know a lot about the internal energy. Now, in order to do this job and make the predictions, one doesn't need to know what the detailed mechanism of the heat-producing event is. All you need to know is that when you have a given set of state properties, those same events will occur. Then one can go to predictions without understanding the mechanism. Now, we really have enough information in what I've said to write down a statement of what the prediction is like. And we'll do that in equation form. First, the J sub P is the production flux, and this will be, for example, in terms of watts per, or rather just plain watts. And that is equal to an experimental constant times the sum, rather the product, of these three variables. Now, the experimental constant has within it the information as to what the rate of heat-producing events is and how much heat is produced per event. That's what makes it an experimental constant. Now, the three things, and they're multiplied by, and bear in mind, all we need to know is three properties to have all the information there is statistically about the internal energy. Any more information is redundant. Okay, the three elements, which intuitively sound right with one possible exception, is that it's the product of the number of candidates for the jump. How many things are there that are going to jump? The next thing is, how often do they jump? The frequency. And the next is a force, the force which drives the reaction. And we propose that this force is the chemical potential of the deuterium in the matrix. Now, that may or may not sound intuitively correct to you, and in the written version of the paper we'll go into this in more detail. But I'll remind you that it makes sense. For example, the driving force for a diffusion reaction is the chemical potential gradient. The driving force for a chemical reaction, a type of encounter, like some others, that driving force is the difference between the chemical potential of the products and the reactants. So it's fairly natural. This is a thermodynamic force. It is not a Newtonian force. It's a force which makes the reaction proceed. Now, just to make it a little more convenient, we do some rearranging and substitutions, and we now have the X heat production in terms of the watts per unit active volume. And we'll talk about what active means a little later. Again, this is a different constant, and the number of candidates is proportional to the D over PD. The frequency we borrow from diffusion technology, and this is the exponential of minus the activation energy over RT, which can be shown to be proportional to the frequency, or the average frequency of jumping. And again, we retain the chemical potential, extracting from either of these equations the three system properties, and so you can remember it for the next few minutes. We're talking about CTP, concentration, temperature, chemical potential for the P. And if we plot this production equation, this is the watts per cubic centimeter against the temperature, we'll see this kind of curve. It's a fairly rapidly rising curve. All three elements affected, but primarily the temperature element. And this curve will extend into, for palladium, hundreds of degrees C, and it will extend into the kilowatt range. Now, we'll do the next one rather quickly. One must know how to impose desired state properties, and I think most of you are familiar with that. Also, nature places any limits. We can't just have any C, T, and P. We've got to be limited to certain things. And I'll just use a phase diagram to show you the relationship. This is old. This is something all of you know. And this particular diagram comes from the American Society for Metals, published during the 70s. And here we are, T, C, P. T, temperature, C, concentration, in terms of D over PD. And in this case, instead of chemical potential, the scale is hydrogen pressure. And this scale is constructed for gas loading rather than electrolytic loading. But the scale could just as easily be the electrode potential for electrolysis. Or both of these things can be expressed in terms of potential. So when I point to this, rather chemical potential. So when I point to this kind of a scale from now on, I'll mean chemical potential. CTP. Now, this curved surface is the surface which distinguishes between the gas phase and the solid phase. Everything below it is solid, everything above it is gas. That's no surprise to you. And the existence of such a surface means that if I know any two of these variables, I can calculate the third. We'll need that a little later. Now, we really don't know enough yet to make predictions because we have a relationship, we know what the temperature versus X heat is, but we don't know where we are on that curve. And that depends on the specific experimental conditions involved. And we have to take another step to determine that, and we will now do that. We have to talk about heat transfer, and when we've talked about that, we're now ready to make a simulation of all these principles. Now, this is one I think we in the field neglect. Now, we've been talking for a couple of days about the cell constants, the heat transfer coefficient of cell, and that's very important. But what we don't talk about is the heat transfer coefficient of the cathode, and that is also very important. In order to measure it, you need to measure the temperature of the cathode, and most people do not. And there's good reason for it. It's not easy. Now this is a heat transfer line for a cathode, and it's simply Newton's law. That's all it is, in which we say the rate of heat loss or heat transfer per unit volume, again, is proportional. These are a series of three constants to a delta T. In this case, the delta T is the difference between the cathode temperature and the cell temperature. This is the temperature, this is the rate of heat loss or heat transfer per cubic centimeter. I show this as a short line. Of course, it's a line of infinite length. That equation goes on forever. And it's really two families of lines. One can have this line moved right to left by changing the temperature of the cell, not the cathode, the electron. Or by changing these constants, one can change the slope of this. And both these things are very large effects, not small effects. I'm not talking 20%, I'm talking a couple of orders of magnitude in most cases. Now, what affects the slope? One thing that affects it, if I'm using rod-shaped cathodes, is the diameter. The larger the diameter, the smaller the ratio of surface area to volume, and the lower the heat transfer. Big effect, not small. The other is the heat transfer coefficient, which is a function of the fluid right outside the cathode. Now, we want to talk about a steady state. We just don't want to talk about heat loss and production. We want to know how do they work together to a steady state or to a point where you know that it's getting hotter or cooler. And for that, we have to take into account both the heat production and the heat losses. And here is one of a family of production curves. There'll be others that go higher depending on what the deal with PD is. The scale here is, again, the cathode temperature. This is the rate of heat loss, heat production, or heat transfer. And here is the heat loss line. Now, what does steady state mean? Steady state really means the conditions under which the rate of heat production, the rate of heat loss are equal and opposite, right? So that happens where this intersects, and you can stare at that for a couple of minutes. You'll find the temperature exceeds this position S will cool. If the temperature is below it, it'll heat, which is the definition of a steady state. Now, take a close look at this curve, because a lot of things that we've been very puzzled about in this field are due to the fact that this is a rapidly rising curve, and this is a straight line. Now, visualize this as a very long curve that goes way up into the next room. Now, as I move this line to the right, which I do by increasing the cell temperature, I go up this curve very rapidly, not slowly. There's a big gain here. Visualize to yourself another thing. What if I move this and then change the slope? Well, can't do it. No way, I can sit down now. I can't start 10 minutes, and then 20 minutes is fine. And for example, the relation to the change in this heat loss curve and the production curve, I believe, is responsible for such things as heat bursts, arc bursts, long bursts. I believe that in the first Fleischmann and Pons work, which pointed out the dangers of ignition and pointed out one that ran away from them. This is the runaway temperature, which I believe happens when the heat transfer coefficient goes down, and the specimen that ran away from them is the one with the lowest surface to volume ratio. Now let's talk about production versus experiment. And as you'll see, unfortunately, the experiments do not measure the system properties I've talked about. The main thing being the cathode, although most of the work does not measure the D over PD. But we can make some interesting comparisons anyway. Now, this work, this development was done in late 1989, and at the time it predicted a number of things would happen in this field. And here are the things, the predictions that did indeed occur. In '89, this was consistent with the existing experiments. It predicted that people in the field would increase their heat intensities, and they did by the following year. It predicted that the new molten salt work would have a very high heat intensity that it proved to have. We utilized, in what I'm about to talk about, work by Makubri et al. And Kitamatsu et al. And their work and this work is consistent, and we use some transferring of current density data to D over PD data that comes from their work. And the latest forced to boiling by Fleischmann and Pons again follows the predictions, and I'll show you what I mean by that. As Dr. Fleischmann left here, let's do that. Okay. Now, let's rerun some of the old Fleischmann and Pons 1989-1990 data. There's paper in it, and I think we don't realize. The top is experiment, the bottom is simulation. This scale, which you can't read, is current density. It goes to 1 at that point. It's 1,000 milliamps. And this is the X power in watts. Same vertical scale. Don't look at that for a minute. The solid lines here represent 15 points, which I call baseline. I call them baseline because they're a consistent pattern. This dotted line is 5, I'm calling non-baseline points, which are the same diameter as this, but simply don't follow the pattern. It's shifted to the right. I think there's good reason for it, but I'm going to ignore these points from now on, and if you get into detail after getting the paper, you'll find that their presence or absence doesn't affect the conclusions under the right hand. Two very dramatic things. We have an order of magnitude change as the current density goes up for a given diameter. For a given current density, we have an order of magnitude change as you go from a small diameter to a large diameter. These aren't small things. Now, this is a simulation. The only difference in the scales is that we're using D over PD. And in most of the work that's been done, there's a pretty fair correlation, at least there's a monotonic relationship in a particular experiment between the current density and the D over PD, particularly in this range, and everything here is in the beta phase. As you can see, the relationships left to right are the same, and the comparison to the curves is about the same. I wouldn't overdo this. I'm not telling you that every point here is on every point there, because don't forget there's an experimental constant in here. What I am saying is the change, these two changes, the big change right to, left to right, and the shape is the same, and that's the sign that the variables are about right and that they work about right quantitatively. If you look at it closely, you'll say to yourself, well, gee whiz, the ratio of the heat between the 1/10, 2/10, and 4/10, very simple. It's about 4 times and it's about 16 times, so it's proportional to volume. And this is the reason Fleischmann and Pons originally used the term specific excess heat. I feel a hot press as the chairman, so I'll talk faster than I should. But this is the same data, except we're plotting left to right is raw diameter. Top and bottom, this is experiment, this is the simulation, and the vertical scale is again X heat relative to the 1/10 diameter. That is, at 1/10, the ratio of the heat to itself is 1. This is a comparison. At 2 millimeter, we take the ratio of the excess heat to that heat. Okay, and these are the experimental points, same ones shown here. This dark line is a calculated line where we plotted against diameter the position the X heat would have if it were exactly proportional to the volume. If it were exactly proportional to the surface area, on the other hand, it would be a straight line down here. Now, obviously, none of these points get anywhere near the proportionality for surface area. So one is almost forced to the opinion that in this case, this is a bulk effect. Now, I talked earlier about active volume. Active volume is the volume where you're getting excess heat made. This says that in this case, the excess heat is being made through the bulk, except it's even better, even more than the bulk, and we'll talk about that in a minute. Again, it's either a little bit more or a lot, depending on the high current density. Here's the simulation. This is the 5-variable simulation of Balmer principles. You now see the same shapes, except lower and higher current density is replaced by lower and higher d over pd. So what's happening is, as a bulk effect, the larger diameter is getting hotter than the smaller diameters because its heat transfer coefficient is a lot lower. And there's an effect of either current density or d over pd, depending on how you want to say it. Yeah. Now, the way things are going, we're about to get our foot come out and pull me in. And gee, I hate to have you miss these gems, but I'll try to do it pretty fast. A fleeting glimpse of commercial X power densities. And this is the forced to boiling Fleischmann and Pons work. They have given us a glimpse of that it is possible to get in the range of commercially competitive X heats. Now, our calculations, which are not in this paper, show that commercially competitive X heat occurs when your X heat, X power density gets in the range of kilowatts per cubic centimeter or multiple kilowatts per cubic centimeter. Now, I think you're all familiar with what they did. They forced specimens to go to boiling. When they went to boiling, and those that had produced excess heat, during the 10 minutes of boiling to dry, actually it boiled to dry in 20 minutes, they measured the heat output in the last 10 minutes, and they got about 3.6 kilowatts per cubic centimeter, which is a very nice high value. The other interesting thing, and we heard some about this earlier today and yesterday, it occurred after the boiling got done. It was during this 10 minutes, most of the cathode was dry, and they noticed the whole cell was hot a long time after that. I believe that the following is happening. What? This is the last color. I'm leaving out 5, but I don't want to make you feel too bad. This is the same phase diagram you saw earlier. Remember, this is T, C, P. I think the Fleischmann ponds specimens were here before boiling. When boiling occurs, the temperature goes up. When the temperature goes up, the gas begins to discharge as must. That's what this diagram is telling us. But what happens fast is that the heat transfer coefficient, when it's dry, goes way down. The heat transfer in the liquid is much faster, even if it's a bubbling liquid almost as boiling, is much faster than the heat transfer in air, which is what they have afterwards. The heat transfer coefficient goes down, the temperature goes way up, goes way above 100. Their cell, they measured at least 300 degrees Celsius in their cell. So what happens is first the temperature goes up fast, the discharge begins slowly. It goes up into this range. There's a 500 degree C line. Finally, the discharge has accelerated and the gas is gone and there's no reason for any exit, X-heat. And this is judging by the heat production equation you saw about 13 and a half minutes ago. Now, I'll make one very important remark, and that is this, that the experimental work now going on is generally in this range. The region for marginally commercial intensities can be seen on this kind of a diagram. Here they are, in this range. The competitive commercially are in this range, and that's where they got for at least 10 minutes. Our commercial goal is to learn how to do this at steady state. And we believe we know how, and one can visualize what a reactor would look like by using these macro principles that I've been talking about. Oh, you're there again? No more of you guys. No, I promised you no more of you guys. The specifics. Boy, you sure know how to hurt it. But, no. I was really All right, now we talked about comparing palladium. If you think separately of these macro principles and what they're based on, nothing I said limits them to palladium. And no doubt there are other systems which do the same thing. Nothing I've said limits it to electrolysis. Quite the contrary. The highest intensity we got here is when we took the cathode out of the cell. Okay? Now, isn't that a strong signal that we don't need simultaneous electrolysis? I'm glad Dr. Fleischer was. Now, when you use the macro principles, you can extrapolate what conditions cause high excess heat. And when you know how to do that, you know how to design a reactor, and you'll think of a dozen ways to do it. I have two kinds of recommendations. One kind to investigators, and that's a recommendation which may or may not make sense to you. It would be probably very good for you and for the field if, no matter how you're thinking about how the game works, think of erecting macro principles in parallel. If you do these together, you'll be surprised how each one helps the other. Second, if there are those in the audience who are potential users, I think this is a path of fairly early practical use. And this is closer than you may think. Thank you very much.
Nice to know somebody is thinking of a commercial application. And those of you who are interested in getting more details, I suggest you speak your tea time. And Bob, which is right here, I think we will proceed on to the next paper. And I just heard news that the after tea session of the calorimetric parallel session will be held in the other room. I think I should confirm it, but please make sure before you go to the session. All good?
I think next time I just asked Dr. Waste to give my talk too. Obviously he took my time as well. Okay, so this is the projected on the back of Pino Pinalasa here. So this is the title of the talk. unfortunate change is Dr. Eagleton's come down with the flu. I had the flu last week, so during this talk, I had intended to have him come up, as I usually do, and show about 5 minutes of very technical stuff on the cells, whatever. And unfortunately, as I say, he is sick. I had the flu last week, and now he's got it. It's terrible to be in paradise and have the flu. He said to say hello to all those who know him here, and hopefully he will be better tomorrow and be able to stay for the talk. But I have plenty of slides, so let's get going here. So that our supporters don't get lost in the shuffle, let me just show them here. Eneco, which is formerly FEET, Produce Processes Inc. of Denver, Colorado, and of course I'm from California State Polytechnic University. It's important to put in Pomona because there is one in San Luis Obispo too, as many of you know. Okay, and now many of us believe that we may be actually finding organized resistance these days. It turns out I have some private intelligence regarding these groups. Here's one of them right here, provided me by Larson, another prehistoric cartoon. And you see these dinosaurs meeting, and they say, well, time for our weekly brainstem storming session. Okay. Apologies to Douglas Morrison and Dr. Nzinga if they're in the audience here. So one of the major questions regarding the light water stuff that Mills really got going and then other people joined in on was the question of whether is this really a light water effect involving protons, or are we seeing just a contamination by the normal component of contaminating deuterium oxide that is in there? About 1 out of every 5,000 molecules roughly is deuterium oxide. And so what we did was we designed an experiment to try to lay this to rest. We ran 2 identical cells, cell 63, cell 64. 63 is a potassium carbonate electrolyte. We have a nickel Fibrex cathode. And here you see the graph of excess power versus current. If we now look at, I should tell you the important feature here is that the cells are identical except they were run in series. This one is nano-pure water-based, whereas cell 64 is dedeuteurated water-based. The dedeuteurated water from Aldrich, and here is cell 64. And now the previous data has the error bars left off, and the cell 64 dedeuteurated water cell has the error bars put on, but you can see the performance is very, very similar there. Very little difference. Okay, and if we look at the analysis of the electrolyte, we find again evidence that the reaction potassium to calcium by picking up a proton is the driving reaction here. And in cell 63 with the nano-pure water, by the way, the cells were run in series, so they always had the same current going through them. But if we look at cell 63's electrolyte afterwards, the concentration of calcium was about 1.1 parts per million. And if I then take my CAF hypothesis and use these reactions with these percent abundance ratios here, the deduced excess heat then from that would be about 1.36 plus or minus 0.14 megajoules. On the other hand, using calorimetry, we actually did determine an excess heat for that cell of 1.11 plus or minus 0.17 megajoules, so that's well within the errors there. For cell 64, the dedeuteurated water had a concentration of 1.14 ppm, and again, deducing it from the cold-alkali fusion hypothesis, we get 1.41 plus or minus 0.14 megajoules. That agrees well with calorimetry, giving 1.51 plus or minus 0.23 megajoules. And now these calorimetric excess heats actually show a favor to the cell 64, which is the dedeuteurated water, and I guess that's just probably within the errors, and doesn't seem to be a real big deal. Okay, so we feel that since using the dedeuteurated water, which cut the contamination component of deuterium down to 1/100th of a percent of what it usually is, that's strong evidence, since the 2 cells then perform equally well, that in fact the light water effect is due to protons and not due to contaminating deuterons. Now some of you may have heard that I have a new model, and I do, and I'd like to invite you to the session, the theory session at 4:30. Of course, many of you are attached here because you're committed to this session. But if you could get to that theory session, you will see a very interesting talk which gets us through the Coulomb barrier, explains a lot about cold fusion. But I still believe in my transmission resonance model, which works in another regime. And you may remember that I predict this kind of scale invariant behavior where we have these hills and these cusp-like valleys here from the model. And we did a light water experiment where we looked for these things. And this was used to predict where the minima might be. These were the actual cusp positions here. This was the first resonance located. You see it was located at 1464 milliamps. It was the fit to the curve was given by an I0 of 10.97 milliamps. This is an equilibrium current in the model. And then the others were located. You can see the I0 values were very, very close. In fact, the average value of this was 11.3 plus or minus 3.54%. So let me show you what these resonances look like. There are about 6 of them here. There are 6 of them. And you can see that even though this looks like it could be fit by a straight line, nevertheless it looks like there might be a cusp there. Okay, so these were taken over the course of a week. They probably should have been taken over the course of 10 hours to all agree. And then going up to the next predicted one, which had a predicted cusp right about here. Okay, this is where it was found, and then the I0 was used to fit it. And you can see it does look like there is stuff going down here. Okay, so if I take the next predicted one up and we do a search, we found it here, and this was fit by another I0 value, very, very close. And again, there looks like there's a cusp in this. And finally down to 200, about 200 milliamps here. And again, you see kind of a cusp. So it looks like this business might be meaningful. More work is obviously needed. The next question would be, is it really related to the light water? And there was a problem with this particular experiment, and that is that we had added 2 cc's of heavy water to the rubidium hydroxide, 45 cc's of rubidium hydroxide. So there is a chance that the behavior seen was really due to heavy water. We need to go back and see whether that's the case, or see whether we can get this kind of resonance structure. Here they are all on one curve. See if we can get this without the added heavy water. It isn't clear that we can. Okay, now some of you have heard of some fantastic gains achieved with the light water, and that's true in our case. And I want to point out that these have been achieved at very, very low input powers, typically say 1/10 of a watt type thing. Here's an example of a light water cell, rubidium hydroxide, no deuterium added. This was calibrated anodically, okay? And here is an interesting series. What makes this interesting is that we had calibrated this cell at 4 different temperatures. We had a calibration curve of 33 degrees C, 36 C, 39 C, and 30 C. And so here are values taken during this week, 211.92 all the way down to 216.92. And you can see here we about 800%, 1,000%, 800%, 1,300%, 1,200%, so on. So these are extraordinary gains. I mean, if you could, in fact, guarantee that you could, well, if I got $10 back every time I gave you $1, as Steve Jones might say, that would be extraordinary, wouldn't it? Okay, he wouldn't say that particular thing in connection with light water out of this, but okay, here are some cases that we looked at with cells running just recently. You can see that this was taken almost 5:30 p.m. on the 4th of December. And you can see that the input power, see where's the input power here, is about 0.02 watts. The excess power was about 0.12 watt for about a 550% gain. Okay, this was, by the way, I should add, this was cell number 72. It was a cesium cell. And I'll explain what this X is in a minute. Okay. Here again is that same cell, looking at it almost 11 o'clock later in the evening, and still about a 500% gain. Here it is No, this is a different cell now, but also a cesium cell. These are both cesium carbonate cells. And this one, we're taking the value at 5:19 p.m. And you can see almost 1,000% gain there, pretty good. Okay. Here it is later, not quite so good. This may indicate burst-like behavior, which I'm going to show in a minute here, about 500% gain. And here it is at about almost 11 o'clock that night, about 650% gain. Okay, now what was the acid I mentioned? I don't have any slides on this, but what we're finding in our own lab is it appears that copper is a cofactor for the light water effect. We haven't definitely shown that you absolutely need copper, but it looks like we have now run nickel cathodes with 10% by weight of copper centered in the nickel, and it looks very much as though we're getting much better results with that. And it's an open question, but we feel at this time we have pretty good evidence that copper is very important. This may mean that some of the negative evidence that we're getting with the light water effect might be due to the lack of copper. Copper, too, by the way, would be to nickel as silver would be to palladium. So remember, Pons and Fleischmann has suggested maybe silver is an interesting cofactor, enhancer, or accelerant in the case of the palladium process. And so maybe we're seeing the same thing with copper in its relation to nickel and the light water thing. Now, I'm going to show you some burst-like behavior. So here is excess power versus minutes now for a rubidium, for a cesium carbonate cell. And these points, this is about 1,000 minutes here, so these were taken about 5 minutes apart or so. But now what we're going to do is take these data points and average them on a longer basis. So we'll average maybe 5 or so of these together. When we do that, you can see what we now get. Still very bursty. And now we're going to average those, maybe 10 of those or so. And now look what we get. And now you're beginning to see a pattern that looks like a heat burst here. And finally, when we make the averaging like 50 minutes a piece type thing, and now you definitely see sort of a heat burst. So what appeared to be bursty on a small scale is, as you go to higher scales, still bursty, and this is very much in consonance with the chaotic aspect that I predicted earlier, and that Srinivasa, in fact, indicated in his letter, which accompanied his very nice summary and review paper of cold fusion results. Let's go to another cell and show that we get this for all of these cells we've shown. So here's cell 72. Again, cesium carbonate. Again, you see this. We've taken data here, maybe one data point every 1 minute or so, or 2 minutes or so. And then if we average these on a higher scale, we get this still bursting behavior. Average those, and now you're beginning to see the burst emerge here. And let's do it with the rubidium cell. So here's rubidium cell. Cell number 69, you see bursting behavior. And now if you average these, then you get this very nice burst, which looks like the burst we saw for the two cesium cells. So we do see these heat bursts, and this is evidence, I think, that we're seeing chaotic behavior of these cells. I think I'll stop there at that point and ask for questions. How much time do you have?
Well, I'm going to show you this deadline, but so we can certainly take a couple of questions. You have stopped.
Dr. Bush,
Yes.
first of all, your calorimetry is differential thermal, is that correct?
Differential thermal calorimetry. We do have a closed cell, so we do have a recombiner.
You've got a
So we have a closed cell. This makes the energy bookkeeping a lot easier to do.
All right, excellent.
The other point is that with regard to the calcium, the Pyrex is Teflon coated, so we don't have problems with calcium leaching out of glass. I
Okay.
think this is one of the criticisms that some of the other researchers have had, in that the Pyrex was not coated with Teflon.
What's your current density on the electrodes?
What's the current density on the electrodes? Typically a few milliamps per centimeter squared. In other words, these electrodes have a large surface area compared to the heavy water case. So typically you're talking anywhere from like maybe 60 to 80 centimeters square of area we can measure.
Okay, well,
There's some shading, of course.
what sort of voltages do you drop across the electrolyte?
Typically about 5 volts or so.
You're one of the just to get there's no information on his presentation on what he's doing, and I think he's doing that.
You don't do light water stuff, so you're interested.
Yeah, exactly. And the last thing is your calorimetry. You're using thermocouples or thermistors for the temperature measurement.
Using thermocouples, we have 2 in the cell and 1 in the bath.
Okay, and what do they process through? Directly into the computer?
The process, well, people didn't know about that, but basically we have a Mac2X thing, a virtual instrument thing that does this.
It's commercial.
It's a commercial thing. It's a high-grade commercial. So, yeah.
One of the things that seems to be necessary for the palladium deuterium experiments is to have things called blanks, or calibrations or comparisons which show zero. I didn't see any zeros in your data.
Okay, you're asking what is a blank here. Basically, you have to realize that the first thing I'll say is that the calibration is checked anodically. So when we get to a particular point in the experiment, we're wondering, do we really have excess heat? We reverse the current. We turn the cathode into the anode and vice versa. And we have checked that against doing the calibration check of the heater, and that checks fairly well at low powers. As you get to higher input powers, those things diverge. Because of the bubble pattern, we feel that the anodic calibration does a better job. Now, I still haven't answered your question.
What does not give excess power?
Well, I don't think that even in the case of the palladium heavy water system, light water system, you have a blank. I think you're just getting excess power that you can't measure. It's just at a very low level. But of course, operationally, you refer that as a blank. I understand that.
Did you ever have any cells which did not show excess heat?
Oh yes, yes we have.
So that's a
I just haven't shown you once. And in particular, a good point here is that a number that did not have the copper Fibrex definitely did not show excess heat.
Would you please explain? I'm sorry.
Okay, go ahead, please.
Would you please explain the anodic
calibration?
The reversal is that you calibrate anodically, no? What do you mean?
Well, basically what we mean is that we put the same power into the cell, but we've reversed the current, right? The current is now, the voltage is negative, the current is negative, so the power is the product of the two, and that's positive. We put in the same power.
Okay.
Do you have any idea as the role of cofactor division?
That's a good question. I think we don't have any idea what the silver does. If you come to my talk this afternoon on this unified model, I'll make some comments on that. So I'll have some comments there. Yes?
Do you get the high power multiplications also at higher input powers?
No, we don't. And of course, this was very suspicious, and it made us completely doubt these things because, of course, the denominator in the calculation of that gain, where the gain is calculated as the output minus the input divided by the input. If you're dividing by a small number, you're very suspicious of that. But remember that the one case I showed you that had the highest gains, we had checked it at 4 different calibration temperatures. So we'd get the effect at one temperature, calibration temperature, and then go to a different calibration curve, still see the high gains, then go to a third one, then go to a fourth one, and see the high gains in all of those cases. It could still be an artifact. But I think that particular evidence strengthens the case that it's a real effect. But we can't be absolutely sure this is it.
I think we have to come forward this point and get to our team. The remaining part of this session will be held in the neighboring room, and we are switching places with the theory section.
Why?
Right, John? Please assemble in the next room at 4 o'clock. Next session at 4 o'clock.
You gotta watch for
All of the sessions, I'm sorry. Right. All of the sessions are running somewhat late. We are running now about 20 minutes late. And I do ask from all the speakers to adhere to their speaking times. And the 20 minutes does include a few minutes of discussion, unless you desire to have more discussion of your paper. The first paper this afternoon
is by T. Mizuno, N. Enyo, T. Akimoto, and K. Azumi from Hokkaido University, Sapporo, Japan. It is entitled Anomalous Heat Evolution from strontium serrate type proton conductors during absorption-desorption of deuterium.
No, I'm going to sit over there.
Field. Paper is going to be given by Dr. Mizuno.
We have reported detection of neutron emission, tritium evolution, and heat production during electrolysis of heavy water using the palladium electrode in a perfectly closed system. Their production rates were rather independent of the fusion concentration in palladium metal. It was suggested that reaction was triggered by the fusion movement in the metal in the first phase. However, the producibility is still poor, and we can't control the reaction because we don't know its mechanism. It is hopeful that some theoretical attempts have been reported, for example, by Charles. He discussed the high possibility of day-day nuclear fusion in solid states building series core. A common system is electrolysis of heavy water and palladium electrode. An experimental difficulty there is that usually charging into the sample needs extremely long time. Takahashi observed heat generation during cyclic changes of current in heavy water electrolysis. This suggests that a kind of perturbation in electric current may be advantageous. Similarly, Yamaguchi reported helium power production from a palladium plate. Its places were covered with manganese oxide and gold plating. In that work, the sample contains relatively low concentration of deuterium, and it was heated up to several hundred degrees centigrade by anisotropic heating. This may indicate that the quick rise of temperatures is advantageous to induce a cold fusion. However, the condition of excess heat generation and other reaction products show very low heat producibility and no controllability. Common to this case, a kind of triggering might be suggested to be helpful in this reaction. The reaction may occur in a chaotic state caused by the movement of proton in the space. In this work, we have tried to use the proton conductor ceramics at suitable temperatures and to apply an alternate electric field. Next slide, please. We use the solid electrolyte called proton conductor. We measure the heat evolution during the neutrino absorption and desorption cycle. Temperature of the proton conductor solid electrolyte plates was maintained at 300 to 500 degrees centigrade. Typically, excess heat evolution of the order of several 10 watt per square centimeter was observed in the presence of deuterium gas under an alternate electric field. Next slide, please. Next slide, please. This is a schematic drawing of the reactor system. Reaction cell is made of the 5 mm thick stainless steel cylinder with 8 cm diameter and 30 cm length. The upper part of the cell is covered with glass cap. A sample was held with platinum plate of 1 mm thickness. Pressed from the both sides, they are fixed to a copper holder. The platinum plate is connected to a stainless steel coated thermocouple. A heater wire passes through several holes drilled in the copper holder. The holder is fixed with the use of stainless steel bolt. This bolt is connected to the bottom of the metal fitting of the glass cap. Next slide, please. This photograph shows a view of the reactor vessel. Next slide, please. The switch ejector line was made prepared as follows. Sample metal oxide were weighed and mixed, and then once calcinated in an electric furnace at 1,420 degrees centigrade for 20 hours. The sample powder was finely grounded and formed into a 1 mm thick and 2 cm diameter coin-like pieces. And then these were sintered in a furnace at 1,440 degrees centigrade in air for 20 hours. After that, sample surfaces were painted with the organic platinum compound and baked at 700 degrees centigrade for 10 hours to obtain a porous platinum film on the sample. Next slide, please. This shows the temperature measurement system. Sample is kept at a constant temperature by means of the stabilized power supply. The electric power is recorded continuously by means of a pen recorder and 2 digital voltmeters for current and voltage. Temperature was recorded by a means of digital voltmeter 0.1 degrees centigrade of pressure. The pressure in the vessel was measured using a pressure to voltage transducer. Temperature versus input power, heater power relationship was calibrated for various gas mixtures. The electric field is supplied from a function generator by a power amplifier, and the current was encoded through a digital voltmeter. Next slide, please. This shows the temperature rise at constant electric heater power. In vacuum, and vacuum gas and hydrogen gas atmosphere, temperature rose steeply after switching on the electric power and reached a constant temperature within 2 hours. Temperature difference between each atmosphere are caused by the heat conductivity difference. The pressure of hydrogen and deuterium are 0.1 atmosphere, but temperature was not much dependent upon the gas pressure. Next slide. This shows the relationships between the input electric power and the temperature in various atmospheres. The phase curves shapes mean that in this temperature range, heat is mainly lost by radiation in vacuum and by thermal conductivity in the presence of gases. And these curves became flat at high temperature, indicating that the radiation becomes predominant. Next slide, please. And this shows temperature changes of the proton conductor sample and the dummy sample. They are placed in the atmosphere of deuterium or hydrogen gas. The sample are heated by the heat of 50 watts up to constant of 380 degrees centigrade with 1 hour. The deuterium gas was then introduced into the reaction vessel, temperature fell down to about around 350 degrees centigrade, but it again started to rise, reaching up to 400 degrees centigrade after 5 hours. And this temperature was maintained at least for 20 hours. In the other experiment in hydrogen gas, with the same type of sample, this dotted curve, or dummy samples in deuterium gas, broken curve, the temperature fell down to about 207 degrees centigrade within 1 hour, and stayed there afterward. This type of temperature fall should well be accounted for as due to increase of heat loss caused by thermal conduction of hydrogen. A small difference recognized between deuterium and hydrogen gas is probably caused by a small difference in their thermal conductivity. The heat generation from the proton conductor in the experiment of deuterium gas was estimated to be approximately 50 watts over 20 hours, or 0.72 milliwatt. Accordingly, the output to input power ratio was estimated to be as large as 7 times 10 to the fourth. Next slide, please. This shows spectra of the X-ray emission spectroscopy. The upper spectrum is the forward sample which generated heat. The lower one is for no heat evolved sample. No difference was noted between these spectra. Next slide, please. These show the difference of diffraction spectra between heat evolved and no heat evolved sample. We can see some differences between them. Next slide, please. These are enlarged picture of the result in the slide. These spectral peaks are not from oxide and hydrogen. The sample was tested after the heat evolution. We don't know whether the peak difference was caused as a result of heat evolution or originally present in the sample. The difference was observed on all of the samples which evolved excess heat. Next slide. We can conclude as shown in this slide. I'd like to argue that the heat generation appeared to be independent of the deuterium concentration. For example, in this case, deuterium concentration in the slit electrolyte is 10 to the minus 3 to 10 to the minus 4 in atomic ratio. We have tried to detect gamma ray using the handy type detector, but no radiation was detected. Nevertheless, we have to use more precise detection system before extracting any conclusion. If we assume that all the heat evolution is caused by fusion of 2 deuterium atoms yielding 1 helium atom, less than 1 cubic centimeter of helium may be generated, as compared with typically 100 cubic centimeter of deuterium gas. Nevertheless, we may have a chance to detect helium nearby a large day super speed. Thank you for your attention. I indicated only 20 hours. already outdated. But I have another excess after that data. But the heat emission increasing slowly and slowly within 30 hours. So after that, I observed some photon data that was completely fine particles. So something wrong with that. Maybe those like heating or hydrogen, everything, I don't know. So maybe 0.7 volume, sample volume, sample sequence around 3 megapixels and concentrate level meaning on 0.2 centimeters.
I would like to ask, how did you test the possibility of chemical reactions taking place and also solvatation energy being present?
So,
did you test?
Chemical test with the hydrogen gas. Yeah, I tested with hydrogen gas. But in that case, I have no heat evolution. Only some kind of reaction with hydrogen gas and the semiconductor. I have no fixed speed.
I make a suggestion here. You have a ceramic and you have 500 watts for the heat assembly power generation. And you have a very poor heat transfer situation in the physical aspects of that. That sort of power generation rate is typical of what will happen when the nuclear reactor, light water reactor. Light water reactors have very high conductivity taking away the power generation. If you interrupt that, we have a gas situation such as you have, which essentially is not very typically that center of the ceramic uranium dioxide will go up into a 5,000 degrees Fahrenheit, 2,500 degrees C within minutes. So I suspect there's many problems.
Did you test for neither H2O or H2O? If you have a mixture of carbon oxides in an atmosphere of hydrogen, we would expect one more.
I beg my pardon. I cannot understand.
If you pass hydrogen through a mixture of carbon oxides at 800 degrees, then we would expect to form water.
Yeah, I think so.
The answer to that is these perovskites are stable under reducing conditions.
Right.
This type of perovskite is stable under reducing conditions. It will not reduce in water.
Even in the presence of nickel, platinum, and high temperature.
Materials of this sort are used for the high temperature fuel cells at 1,000 degrees Kelvin or centigrade, excuse me.
I have a suggestion. One should take the sample after the heat has been obtained, the excess heat, and a witness sample, identical, without having deuterium put into it. And then afterwards, treat both, for instance, with chlorhydric acid and measure how much energy comes out in the tube. And that there will be a difference, maybe equal with the amount of heat that has been obtained.
Thank you very much again. Thanks, Todd.
Srinivasa, Ramamurthy, P.K. Luciati, and P. Adibabu from the Nava Atomic Research Center. Today is entitled to Studies on Ecstasy Generation in Nickel H2O Electrolysis Cells. Paper is going to be given by Dr. Srinivasa.
Further studies on excess heat generation, and maybe I'll be presenting the results since the Nagoya meeting. The work was mainly carried out at the Process Instrumentation Systems Division, and Dr. Ramamurthy was the electrical engineer who took care of the instrumentation at that laboratory. The cells up to the month of May 93, we used silver double-walled vacuum viewers, essentially commercial thermos flasks, which I described at the Nagoya meeting. Since May 93, the above flasks were desilvered by breaking the vacuum between the two double walls, because we wanted to get to a transparent cell and also be able to go on to slightly higher power. So we had to purposely reduce the sensitivity of the system. This is a diagram of what I call the see-through cells. This is the nickel platinum electrode assembly, and this represents the, actually it's not nickel, it's manganese heater coils, and the whole thing is just placed in the ambient atmosphere. And this is a glass beaker in which we can keep it so that when the cells are operating, we can observe the electrolysis. This is a sketch of the electrode assemblies. Most of the experiments we carried out with a flat plate assembly. This is just a simple Teflon frame into which there is a slot where the nickel electrode is kept, and this is a platinum wire. In some of the recent experiments, we had another design, what we have called as a sandwich design. We have two plates of Teflon with perforations. The nickel is kept in between, and the whole thing is bound together as a package using the platinum wire. A very simple arrangement. Note that in some of our experiments, we have also used platinum foil, so that there will be a 3-layer system, or in this there will be 2 grooves, and there will be a parallel plate, nickel and platinum foil. Most of the experiments were conducted with nickel, and we have used 5 types of nickel, which are named as follows. I will very briefly describe it. The stuff known as Nair nickel is a porous, sintered form. It is sintered from the powder, nickel powder. It is fabricated at Bath by this gentleman. He has been making hydrogen generating plants by the electrolysis of KOH. So these were readily available when we got into this. What we call as Totlani nickel is deposited electrolytically onto a stainless steel rod, and then it is peeled off. And this type of nickel foil is fabricated for us by this gentleman, Dr. Totlani, at the Metallurgy Division of Bath. The third type is known as the ESIL nickel. ESIL stands for the Electronics Corporation of India. They are a public sector undertaking manufacturing nickel cadmium batteries. So this nickel is a porous type of nickel which we just picked off the production line. What we call Bush nickel is the same type as what Robert Bush uses, procured from, this is the Fibrex mesh, made I think by national standard in the US. And finally, a solid nickel is just a rolled nickel foil. It's from some firm in UK, but it's not, I think, Johnson & So 5 types of nickel we have used. The electrolyte study were potassium carbonate, sodium carbonate, lithium carbonate, both natural and enriched. Lithium 6 enriched to 54%. The purity of the materials used are analytical reagent grade. Usually they contain about 20 ppm of calcium, and that's important for you to note. I'll come back to that later. Typically we operate 5 cells in together in a band. They are operated with separate power supplies. They are made in a series of parallel. And there's one dummy cell which is used as a reference cell. And the whole thing is kept in an enclosure covered by a transparent plexiglass covering for safety. The calorimetric technique is very simple. We use copper constant thermocouples for temperature measurements. There were typically 2 thermocouples in each cell, one in the upper region of the cell, one in the lower of the flask, one in the lower region. Typically the difference between the 2 thermocouples was less than or equal to 0.6 degrees. No stirrer was used in any of these experiments. We had difficulty driving a stirrer through the commercial thermos flask. The only stirring was during the electrolysis due to the bubbles. And voltages, currents and temperatures were continuously recorded at 2-minute intervals using what we call a Yokogawa hybrid analog digital system, which is hooked up to a standard personal computer. The ambient room and enclosure air temperatures are also monitored and recorded. Typically the cell time constants for attaining equilibration with the silvered vacuum dewar flask was typically 24 hours, and with the desilvered flask, because of the lower sensitivity, it was equilibrating within 8 to 12 hours, depending upon the power put in. The analysis is again standard. The delta T is measured as the average temperature of the cell. That should be T1 plus T2 by 2 minus T reference, which is the reference cell. Input power in the case of heater is V into I. In the case of electrolysis, since we are using open cell, it is V minus 1.482 into I. Is all quite standard. The sensitivity or the calibration constant in the case of the silver vacuum flask, the calibration curve was highly nonlinear, varying somewhere between 21 to 34 degrees C per watt, whereas the desilvered flask which we used subsequently, we used to get very almost linear curves in the region of 7 to 10 degrees C per watt. At this point, I would like to quickly go through the slides, just to give you an impression. These are just a few slides, so it doesn't matter. Now you can see the 5 flasks, and this is the Perspex safety enclosure. This is the Yokogawa recorder and the computer on that side. This is Mr. Ramurthy, who was responsible for the entire instrumentation. Next slide, please. These are the 5 flasks which we are using. The same flasks are desilvered. They are just commercial flasks, hardly $2 each or $3. And sorry for the messy wiring here, but it works. Next. This is a close-up view of one of the cells. This is, in this case, we varied the amount of platinum wire we used. There was some discussion about the total length of platinum we need. This is a very low, only 3 coils here. But in most of the experiment, we had some 10 or 15 coils. This is a manganese heater coil encased in Teflon tape. Next. This is another view of a couple of years. We have more number of platinum. Here the ratio between nickel surface area to platinum is adjusted. This is one of the porous nickels manufactured. This is a Nair nickel. Next. Another view of 2 more electrode assemblies. Next. This is a typical curve. This result was presented at the Nagoya meeting. It's not in proper focus. You can see the highly nonlinear nature of the calibration curve. The power range was typically between 0 to 1 watt, and at 1 watt power we used to get a temperature difference of about 25-30 degrees. I will mark next. These are Nagoya results, just to give you an idea of what an XSE is like. This is the calibration curve, along the curve, and these are the XSE points. Note what is pointed here on the x-axis is the input joule power, V minus 1.482 into I, and this is the delta T. These are the points with calibration. And for those who ask for, since we don't have stirrer, many points were also obtained with what we call anodic calibration or reverse electrolysis. Bob Bush was also talking about it. Invariably, reverse electrolysis points also fall on the heater points. And these are the electrolysis point. And when we talk about excess power in this case, at 10 degrees C, if you get a point, actually we are putting in about 0.2 watts, whereas the input power is only 0.1. I would say that point is approximately giving you 100% excess C. This is the kind of analysis. Let's go on next. This is probably the last of the Nagoya series, just to show you some of the earlier results. Next. Okay, now I come to the new results. Now, this is the last of the Nagoya series papers. What I wanted to show here is at that in the proceedings, we have claimed at that time out of 18 cells, 16 cells showed excess power. This column indicates kind of excess power we had indicated, and it was rather high reproducibility. Now this is a broad overview or summary of the experiments carried out since the Nagoya meeting. You see here, from 29th October to 2nd January, we ran 3 series of experiments, one of the XD, XD and XC series, in all 5 cells and 40 runs. But to our surprise, there was absolutely no excess heat. What had happened was, during my absence when I was away at Nagoya, the engineering charge had replaced all the copper Constantine thermocouples with stainless steel clad. They were much more sturdy, looking very neat and professional, and nobody expected it would have any different, but we had no excess heat at all. We made every effort to see that the Nagoya cells are in the same conditions to reproduce. The only difference was the thermocouples. So with great reluctance, we pulled out the stainless steel clad thermocouples and went back to the copper Constantine thermocouples, and lo and behold, all 5 cells started showing excess heat. Now this is relevant. I was very happy to hear from Bob Bush today that copper plays an important role. Just 5 minutes ago I was talking about it. I was very happy to hear about that. For some strange reason, the presence of stainless steel kills excess heat. So we wasted about 2 months on that, but all 5 cells here showed excess heat. Again, there was a third phase. These are the 4 phases we went through. Again, there was a third phase for a period from 6th of March to 9th of May. There was I will not say there was no excess heat, but the calibration curves were very scattered. The points were going up and down, and we traced that to a fault in the current measuring system. So this was faulty instrumentation. Since 10th of May, we have had 5 series, and again we have started seeing excess heat. I will be summarizing the results of the phase 2 and phase 4 in the following slides. On the whole, the overall success rate in the phase 2 and phase 4 is about 50%. 14 cells out of 29 have shown excess heat. I will very quickly go through these curves. They may be a little boring for you, but I'll just flash through. This is during phase 1, the XD series, when the stainless steel clad thermocouples were used. There's no excess heat at all. You can see the calibration curve as well as the electrolysis points are more or less. We do not claim any excess heat. This is just one sample out of 5 such cells we ran. No, 5 into 3, 15 such cells. There are 3. This is cell XF1, the first of the new cells which started showing excess heat once again. As I mentioned, this is how one measures the percentage excess heat. This quantity A by B into 100 is the excess heat percentage. We were continuing to quote excess heat in the form of a percent. The percentage excess heat for each of the different points will be different. This is the calibration curve. These are the note that the power in this case is up to a maximum of 2.8. I will quickly fast through another 4 or 5 such slides because they all look similar, but just to say that the large number of cells have given us. This XF2 is a porous nickel cathode. This is a Nair nickel, platinum wire, potassium carbonate, and this time the linearity is slightly more linear. And for this point, for example, one would say the excess heat is about 100%, and otherwise nothing special about this. You can proceed. Now I'm going to show you the same XF2, same results, plotted with slightly different conditions. These are the initial points which showed us excess heat. What we did in this was introduce a stainless steel rod into the system. It was working, no other change, and these are the blue points. The excess heat vanished altogether. At this point, we took out the stainless steel rod after the stainless steel tube and changed the solution, and once again we have started seeing the excess heat. So this is how we learn to avoid stainless steel in our cells. This is cell XF4, shows about 0.4 watts. This was a cathode which was used earlier in the results presented at Nagoya. Once again, it has been repeating itself. This was a lithium carbonate, but here the anode is in the form of a foil. This is a parallel plate geometry. This is important because I think some protocol was distributed by Ed Rothwell which suggested that one has to maintain a very high ratio between the cathode and anode, we find that is not very important. This is a solid nickel cell except 5 sodium carbonate. The same cell which is working with sodium carbonate, the sodium carbonate was drained out, and once again potassium carbonate is put in. The magnitude of excess heat was more or less the same. Now I am not giving you magnitudes here. I know. Time flies fast when you are here. Now we come to the first of the desilvered flask, and for the first time we appreciated that the excess heat points were really parallel to the calibration curve. In the previous cases, we didn't know, because now that looking back it is obvious, but once we went to the desilvered and the calibration curve became linear, we find that the excess heat, which is about that much, is independent of the input power. In this case, it has gone to a maximum of 5 watts. This incidentally used a sandwich assembly. Well, again, I will go fast through another 3 or 4 such cells. These are results from May, June. Once again, this is a cell XF1, total nickel, natural lithium carbonate, calibration curve, a parallel curve. Cell XN5, Nair nickel, slightly different, potassium carbonate. This cell was repeated with a number of other electrolytes also. I have not plotted those points here. But whether it is potassium, lithium or sodium, we seem to be getting the same amount of excess heat. The interesting thing here is that these were the points initially. It's a very small excess heat in this particular cell. At this point, we took out the cathode. The entire cathode assembly was put in a bath and cleaned in an ultrasonic bath, and once again put back, and the excess heat magnitude has gone up, showing that the surface purity level of the cathode is very important. Of course, it was not always success. The XP series, suddenly all 5 showed no excess heat at all. We don't know what mistake we did at that point. You can see here there's a period of 1 month of frustration, or about 2 weeks of frustration here. Electrolysis and the calibration points were in the same curve. So we drained the electrolyte, started afresh, and XQ series, once again we started C, and in the XQ series again, with the working cell, the electrode assembly, flask, everything being the same, only the electrolyte was changed. You can see that lithium carbonate, enriched lithium carbonate, potassium carbonate and sodium have all shown excess heat, except that the potassium carbonate seems to be slightly higher. I think I should go on to conclusion now. This is a summary, large amount of data here, but just to give you an idea, summary of the post-Novayo experiments covering the period January to August. The XF series, the first one, we started giving us excess heat, then we learned to avoid stainless steel, and somewhere down the line the XM, somewhere here was the desilvered flask, somewhere here. Up to this was the conventional thermos flask. Some have shown in this XF series, every cell showed excess heat. In the XP series, none of them showed excess heat, but in other cases, roughly 2 or 3 out of 5 have been showing excess heat. And this gives the total number of cells, 5 cells and 180 runs, a large number of experiments, and to confirm that this kind of cell, open cell, does indeed give excess heat. Now before I come to the conclusion slide, I want to flash a slide which I showed yesterday at the tritium measurements. The electrolyte in some of these cells since the month of July were analyzed for tritium, and this shows the tritium contained in 8 out of 17 cells have shown tritium to an extent of about varying from 30 to 300 dpm per ml. Yesterday I explained what precautions we took to make sure that this was real, but purely by coincidence that most of these cells are all lithium carbonate cells. However, there has been at least one potassium carbonate cell which has given tritium, and my experience is that whether it is lithium, potassium or enriched lithium or D2O, we always see tritium. And to see if there is a correlation between excess heat and tritium, you can see that these are the excess power points. I hope I'm not covering it. This is the tritium point. So here we have tritium in cells which have also shown excess heat, but these are all cells in which there was no excess heat, but it has shown tritium. The last 2 slides, the conclusions. 14 out of 28 open nickel H2O cells have shown excess power. We have not studied closed cells so far. The absolute magnitude of excess power has varied from about 0.2 watts to 0.8 watts, and the input power has been less than 6 watts, but usually in the 1 to 2 watt range. The excess power is found to be almost constant for a given cell and a given surface condition of the nickel cathode, and it is independent of the input power or cell constant. So there's no, really speaking, there's no point in talking about a percentage of excess heat. However, to impress people, we quote the percentage at a lower input power. So the maximum excess power absorbed by us at a lower power end is typically around 0.2 or 0.3 watts input is 110%. The excess power has been observed with all 4 electrolytes, presence of stainless steel. I am told, incidentally, Randall Mills has very clearly indicated that you should avoid chromium, and maybe it's the chromium in the stainless steel which kills the excess heat. Ultrasonic cleaning and anodic operation, that is reverse electrolysis, often switches on the excess power in a cell which normally, when you switch it on initially, if it doesn't give excess power, this helps. Excess power is observable on the first day of cell operation in most cases. That is the beauty about these cells. There is no such thing as loading. If it doesn't work in the first day or two, you might as well give up and look for some method of improving it. Now, of course, the Faraday efficiency was measured in many of the cells, not all the cells. Typically, it was more than 95%. Hence, recombination is definitely not the cause of excess power, especially when the excess power margins of 50 to 60% or 100% as we claim. Remember that it can be very simply shown that the apparent excess power fraction, the excess power, can be shown to be given by this expression F by V by 1 minus S, a simple juggling of the numbers. You will find where F is the recombination fraction. Note that when the voltage applied is more than about 3 volts, this ratio is 2 minus 1 is 1, and you will find that the denominator is greater than 1. Therefore, in other words, in order to show 50% excess heat, one has to account for more than 50% of recombination, which is very, very difficult to explain. 40% of the cells analyzed indicated tritium to an extent of 30 to 300 dpm per ml. Great precaution was taken to ensure no contamination is possible during either the sampling, distillation, or counting. It was ensured that fresh electrolyte does not show any counts. After the month of July, we made absolutely sure, before even loading the cell, that there was no tritium in it by double checking it. These tritium results are presented as well. Thank you very much. I think
I have discovered last year a non-nuclear source of excess heat, and we need to subtract it in order to get the true nuclear.
yeah, I have seen your paper on that. Maybe I should discuss that amount. I have no idea how much it contributes nowadays.
Published sometime last January or something like that. I'm cooperative with US because of all things
Do you think you can explain about 100% of excess heat by this mechanism? I agree. Sure, yeah.
True nuclear.
I agree. I should look into that.
What metal did you use for your cathode leads, and how did you attach those leads to the Fibrex?
In the cells, trombate was just mechanically coupled. No, we didn't know solder was permitted. Spot welding was tried. In the case of Fibrex, it was a little difficult at bonding. But mechanical coupling was the best, just with a nickel wire. Nickel wire was used. And all metallic leads above the electrolyte level were covered with a Teflon or PVC. No bare metal was exposed. Both the platinum leads and the nickel leads were completely covered to avoid the possibility of deformation. Well, as I said, there are different methods of production. Some was a sintered nickel, some was electrolytically deposited, some was a solid rolled sheet. Like that, there are different ways of producing them. No, we did not make a very thorough analysis on gate. To be honest with you, we did not bother to do that. Maybe we should do it in future. So we were really interested in making sure that these excess heat or the so-called excess heat is reproducible and it is there. And since the magnitude is quite large, the next step, of course, is to do it in a closed cell. However, I've heard that Robert Bush and other people have done it in a closed cell. Randall Mills has done it in a closed cell. If the chairman permits, I can show one slide of Randall Mills' result. Okay. Okay, that's all. Thanks.
I'll speak loudly. Do you have any information about the temperature dependence of this phenomenon?
There were a few cells. Let me answer the question in two ways. We need here that Randall Mills finds that the optimum temperature is about 60 or 70 degrees. In our case, we did find that in some cells, although most of the cells showed apparent current, in some cells as you approach higher temperature, that did appear to go up. So it has to be explored. What is important is this flatness of the curve related to the XC curve calculation agrees with the findings of Randall Mills, but does not agree with the results of, I think, Matoya. She finds that it is the percentage, I'm not mistaken. She gets a constant percent, not a constant absolute magnitude. He finds the constant absolute magnitude.
Next month we end This presentation will be entitled, or is entitled, Cavitation-Induced Microfusion to be presented by Rogers from Equus Science. And Dr. Russ George at the same time.
We have today. I wanted to introduce, with my partner Roger Stringham, a new method for producing some interesting effects in deuterium and metal systems. And first, let me give you a little introduction as to how we arrived at this point. Both Roger and I have been working independently, and this year together, keeping track of the cold fusion phenomena ever since Hans and Fleischer introduced it back in '89. Roger was working back in '89 in the field of sonochemistry, and upon hearing of Hans and Fleischmann's results, surmised that some similarly interesting results using deuterium and palladium might be seen using sonochemical methods. He began his first experiments in April of '89 and immediately observed some very interesting results. And I won't go into the results right now, because Roger will cover that, the experimental results in a moment. But the best way to describe how cavitation systems can produce these interesting results is to show you a computer animation that we produced. So if you'll roll the videotape, I'll show you that. This is, in this system on the left, you have heavy water and a sonicating horn producing bubbles at 20,000 cycles per second. And on the right is the palladium foil. As the bubbles are produced in the liquid and come into being and expand and collapse in sync with the acoustic wave. Here's what these are actual microcinographs of a collapsing bubble on a surface as the acoustic pressure wave passes through. And as you can see, the bubble collapses, forms a jet, and the contents of the bubble are injected into the surface. This is a little close-up of it. This is with the collapsing bubble forms, and as the bubble collapses, there's in our system 10 to the 13th deuterons collapsing and injecting in a half-micron site on the palladium lattice. And what we have observed, what we think, we surmise, is a deuteron comes in, meets a resident deuteron in the lattice, and forms a helium-4. And somehow the energy is released into the lattice. One of the other reactions we've seen is production of cadmium-114, which we surmise may be as a result of the deuterons forming into an alpha and combining with palladium in the lattice to form cadmium-114. We're not certain about the theoretical mechanisms at play, but we're quite satisfied with the results. So that's actually the end of the video. I can go on to show you a few view graphs.
What's he saying?
So when the bubbles form, we're forming millions of bubbles, 20,000 times a second, all over the surface of the palladium in the system. One of this is a actual photograph, microphotograph of a cavitating bubble on a surface. And as you can see from the photo, as the bubble collapses, it forms a torus, a jet. And the contents of the bubble are injected with substantial power into the energy into the lattice. This is published in February of '89 in Scientific American. Photograph. This comes out of the some chemistry field. So that's actually our cold fusion mechanism that we believe, or microfusion mechanism, I should say. Sometimes when we do that in our system, we cause some changes in the palladium. This is a palladium foil, 5 centimeters on an edge and 1/10 of a millimeter thick, that melted in the heavy water system. And we've seen this result a number of times. And analysis of the material shows it's very clear that melting occurred. And indeed, it's in a heavy water system where the heavy water is flowing through the system. It's both the reactive fluid and the coolant fluid in the system. So we believe this happens very quickly. We believe in the system. And we don't like this result to occur in our system, as it burns up the palladium and ends the experiment, and it's an expensive demonstration of the system. When this occurs, we recently did some scanning electron microscopy on that very sample, and we found in the sample, upon looking at it, small sites on the sample where there are little since we're in Hawaii, they're like little volcanic vents where we believe hot material has, a hot microsite has formed deep in the lattice and ejected hot material out of the lattice. So that's what it looks like, and I'll pass you over to Roger, who can discuss some of the results of our experiments.
Well, thank you for being here. It's a big crowd. I'd like to examine the bubble. The unique thing about this system is that there is extremely high energy focused in a very small volume. Now, and the idea is getting this energy onto the lattice. Now, if we start with a 50 micron bubble, which we started with a 50 micron bubble. It can collapse to 1/100th of its radius in less than a microsecond. And that gives you a volume change of 1 million